addition principle is this. Suppose an activity can be done in N sub 1 ways, and a second activity can be done in N sub 2 ways, and that these events are mutually exclusive. So remember, mutually exclusive events are if one act is performed, the other cannot be performed, okay? So if I'm driving to work, I can't be riding a bike to work. Those are mutually exclusive. Another example would be when tossing a coin, getting heads and tails. That would be mutually exclusive events. So let's suppose we flip a coin 5 times and record the strings of tails and heads. How many of these sequences have exactly one head or one tail? So there could be 5 possible strings with exactly one head, right? Because I could put the head in any of these slots. And the same would be true for tails. Like the tail could be here, or it could be in any of the other 4 spots. So it'd be 5 plus 5, which is 25. Sorry, which is 10, because we aren't multiplying. It's 10. And these are mutually exclusive events, because if you have exactly one head, you've got 4 tails, and if you have exactly one tail, you have 4 heads, and so they can't occur at the same time. Next, I want to know how many of these strings begin with 2 heads or heads, tails, heads. So how many strings could be heads, heads? So I've got heads, heads, and then I have 3 blanks, or I have heads, tails, heads, and 2 blanks. Well, I've got 2 choices for this 3rd entry, 2 for this 4th, and 2 for the 5th. So there are 8 possible strings that could start with heads, heads. For heads, tails, tails, I have 2 choices for my 4th flip and 2 choices for my 2nd flip. So there are only 4 possible strings that start with head, tails, heads. Because these events are mutually exclusive, it couldn't start with heads, heads, and heads, tails, heads. We add these together to get 12. The inclusion-exclusion principle is something you've seen before. I believe we talked about it with like Venn diagrams, okay? So let A and B be finite sets. Then the size, the cardinality, right? Let's think back to section 1.4. The cardinality of A union B is the size of A and the size of B minus the intersection. Okay, so if I have, let's let this be A and let's let this be B. So let's let the size of A be 10 and the size of B be 7 and the size of A intersect, that's an intersection, let me clear that up, and the size of A intersect B is 3. So I know, 3 is in here, okay? All of A has to be 10, so there's going to be 7 in A that are not in B. B has to have a size of 7. I've already got 3 in here. Here's A intersect B. Okay, so I have 4 over here. Now, if I want to know the total sum of what's in A union B, that's going to be 7 plus 3 plus 4, which gives us 14. Do you agree with that? Now, what if I didn't want to sketch this beautiful picture? Well, I could use the inclusion-exclusion principle. So the size of A union B equals the size of A plus the size of B minus the size of the intersection. And this is so those elements that are in both A and B don't get double counted. So this gives me 10, because I substituted in, plus 7 minus 3. So I get 17 minus 3, which is 14. Ding, ding, ding. The inclusion-exclusion principle works. That's why it's a principle. So let's go through an example. I think we did this exact same example in finite, but I really liked it, so we're going to do it again. In the year 2000, Executive Magazine surveyed the presidents of the 500 largest corporations in the U.S. Of these 500 people, 310 had degrees of any sort in business, 288 had an undergraduate degree in business, and 184 had graduate degrees in business? How many presidents had both undergraduate and graduate degrees in business? So I told the union, right? They give me the union of S. Let's let S be presidents with an undergraduate degree in business, right? And 238 is the size of S. And they tell me the number that had graduate degrees, so the size of T is 184. They tell me the union, but what they don't tell me in this case is the intersection. I want to know how many presidents had both. So I already know S union T, but I can use all this information to find S intersect T. So I would have S union T equals the size of S plus the size of T minus the intersection. Now I have 310 because I'm substituting in equals 238 plus 184 minus the size of S intersect T. So if I have 238 plus 184, that gives me 422. And if I subtract 422 from both sides, that's going to give me a negative 112. Let's move this up here. Negative 112 equals negative S intersect T. So we divide both sides by negative 1, and I find that 112 is the size of the intersection. So 112 presidents of large corporations have both graduate and undergraduate degrees. Here is it all worked out. We got the correct answer. I think in the last class we used N of S as the notation for cardinality. Now we're going to use the two vertical bars like we saw in section 1.4.